Okay, welcome everyone. This is going to be the last bit of our preliminary information. We have talked about various things in getting ready for our first real physics concept of constant velocity, position, displacement, but the first lab that we're going to do involves this concept called constant velocity. So today we're just going to do a summary of all the things that we've talked about, as well as talk about how I'd like you to do your lab reports when we do labs, okay, projects. Okay. So the first thing we have talked about is estimation. And please take notes accordingly. We have stated that estimations are educated guesses. They're order of magnitude guesses or estimates. So every time we get an estimation, we are going to express it in some sort of power of 10, 10 to the x. You know, how many marbles can fit in the earth, how many marbles can fit in a flask, a beaker, like we saw on the first day. And we had a method for solving those types of problems. So the first method of estimation involves a question or statement of the same geometry. How many of these small volumes can go into a large volume? How many of these small areas can go into a large area? The same geometry. How many of these small lengths can go into a larger length? So length, area, volume. So those are the first type of problems that we had. And so those are, in this method, question statements of the same geometry. So in this method, we wanted to figure out how many small somethings, how many small objects can go into a large object. And so we would normally calculate the volume or the area or the length of both large object and small object. Then we would have the large object in the numerator divided by the small object in the denominator. And that method again looks like this. So we have large, whatever length, area, volume in the numerator. Typically, when we had the marbles, how many of the small marbles can go into a large volume of a room or earth or something. And the small is on the denominator. And it could be a small length on the denominator, large length, numerator. Just depends. And most of the time we've been working with volumes. Large volume over small volume, we can get the estimate and report it in a power of 10. Okay, for example, how many small marbles can go into the earth? We're comparing volumes. How many blades of grass can fit on a 8.5 by 11 piece of paper? We're comparing areas, or how many small segments of sticks or something can go into, a tree trunk. So we're comparing lengths. So it just depends. The first estimation method involves a question or statement of the same geometry. All right, and then our second method for estimation is a question or statement of between two different quantities. I'll explain that here in a moment. For example, we wanted to estimate the number of breaths in 1 million years. The quantities are breath, years. So when we have two disparate quantities, there's a particular method that we can use to solve these type of problems. So the example would be estimate number of breaths in 1 million years. And our example in the book was 70 years or 80. I'm going to extremize it a little bit. So the method here is start off with something that we know. We know 1 million years. That's in the statement. And then we go from what is known to a reasonable assumption that involves the quantity we're trying to figure out, which is in this case, the number of breaths. So a reasonable assumption would be 1 breath we take basically every second. And so we can whittle down what we know, which is the years, into number of seconds by breaking everything down by conversion factors. So just to show that again, we have a known quantity, which is 1 million years. And then we're going to go from known to a reasonable assumption by way of successive conversion factors. So known to reasonable assumption, because we can take the years and break that years, which we know we want to get rid of that and get to the unknown breaths, which is in the assumption, the reasonable assumption. Our reasonable assumption is 1 breath every second, or we can just say second. So we know that years and seconds are units of time, so we can just break down years. Okay, 365 days in a year, and 24 hours a day, until we get down to seconds. And the only thing that's left is the breaths. And then we have our reasonable estimate, our reasonable guess, and expressed in the power of 10. All right, the next thing we talked about was the difference between accuracy and precision. In English, it means the same thing, but in physics, it has a distinct meaning to it. Accuracy and precision. So quickly, trying to use the Wu Wei philosophy as much as possible. Go look that up sometime. Accuracy how close any measurement, like you're in a lab and you're trying to make a measurement of the gravitational field strength or the acceleration due to gravity on the Earth, and you know the accepted value is 9.81 meters per second squared. How close is your measurement to that accepted value? Determines the accuracy. The closer, the more accurate. Is an accepted or known value. And those things are going to be important because we're going to have something called a percent error, where we're going to compare the experimental result with our known result and see just how good our experiment actually was. And then if our percent error, for example, is say 20% or less, ideally 15, 10%, then we can say just by the numbers, by the data itself, that our experiment was pretty good. Because our result was a pretty fair estimate, a pretty small percentage between the relative accepted and experimental quantities. You may have seen that before, and we'll be doing that in here. So accuracy, how close a measurement is to an accepted value. Precision deals with number of significant figures and a result. The more sig figs you have in your results says something about your instrument. Like I had the example of the meter stick. We usually typically measure the centimeter/millimeter side of the meter stick. We don't look at the other sides because they don't have as much divisions. And that means that you're not going to get as much precision as you would on the centimeter side, because there's more gradations on the centimeter side, centimeter/millimeter side. So you want to have an instrument that has a lot of detail to get more precision. So number of sig figs in a result says something about your instrument. I'm going to do instrument for short. Yeah, so the more precision, your instrument is very detailed. Okay. So there's that. Now, an accuracy example. Okay, we've seen this before. Let's say that our accepted value for the acceleration due to gravity is going to be 9.81 meters per second squared. We'll become comfortable with those units in time very quickly. Why do we associate meters per second squared with the units of acceleration? You will know. So this is our accepted value. Let's say that student group 1 gets 7.89 and 2 gets 8.96. Well, it's student group 2 that's more accurate because it's the closest. I think. And they have the same amount of precision. Same sig figs. Now, precision example. So we're still comparing the accepted of top here, 9.81, and then in student group 1, or just another day, student group 1 gets 9.81, and dead on accurate, and then the other one gets 9.806354. Well, the first one is completely accurate. It's right, you can't get any closer than that. It's a bullseye. The closest. The second student group is slightly less accurate, but pretty good, but more precise than the first, because we know that precision deals with number of sig figs. The second one has 7 sig figs. We count the leading digit and everything after the decimal. If it was a 0, we only count everything after the decimal. And that would be the most precise, the second group. And this would be accurate, but less precise. And this would be amazing, but slightly less accurate. That's okay. In some context, okay. Slightly less, oops, accurate. Try not to scroll down because I want to keep it here. But yeah, more precise, right? They're relative to each other. So 2 is more precise than 1. 1 is more accurate than 2. And we have a question. No, we have not taken notes like this before, not with simultaneous quarantines and people here for the person. Yes, yes, exactly. We got this. Okay. The next thing, sig figs calculations. We did a brief introduction into what is a sig fig, how do we count number of sig figs, you know, all that good stuff. I just made an allusion to that just a few seconds ago. We don't count any leading zeros. We count everything after the decimal. But if we have a leading digit, we count the leading digit and everything after the decimal. And we have some other tricks of the trade in how we calculate sig figs. We, you know, one thing to determine number of sig figs is to put the number in scientific notation, and then that'll determine how many sig figs we got. Right? And we never look at the power of 10 in the sig fig result. We just look at the number before the power of 10. So with our sig figs calculations, we had a couple of methods or rules. We are multiplying and dividing in our sig fig. The result should not be more precise than the least precise number to produce that result. In other words, the answer should be in terms of the least number of sig figs. And so that's what we were banking on when we multiply and divide. I'm going to be glib right here just for the moment. The result should not be more precise than the least, than the least precise number to produce that result. That's wordy. Or answer in terms of least sig figs. For example, 75 times 22, the answer should be in terms of 2 sig figs. Calculate that. One second. Your calculator will say 8,250, but you know, you want to make that into 2 sig figs. You can say 8.3 times 10 to the third. You know, just try to get it down to 2 as best as possible. it doesn't count the power of 10, because it could be zeros here in the 10 to the third. It could be zeros. It could, as we see here, a 5 and a 0, a 250, but we just don't know. So that's why we don't count that. All right, and so we just do the 8.3. So the answer to sig figs. So again, like I said, this is all summary, and before we launch into doing labs and in-class projects and stuff, which we will have to embark upon these things that we've been doing in our labs. We have to do proper sig fig calculations, doing estimates, and knowing how to read accuracy and precision, and doing estimates, all that. Okay. So moving on to adding and subtracting. I think I'll save the writing. We know that when we add and subtract numbers, that the answer should be in terms of the least number of digits after the decimal. So, for example, if I have 158.1 plus 85.14, we don't look at the sig figs per se, although we can make an argument for that. We just look at the number of digits after decimal. I try to, hopefully that's an easier look, but everybody's gonna possibly approach it in a couple of different ways. But the answer should be in terms of one digit after the decimal. So if we do that addition, 158.1 plus 85.14, 243.24, so 243.2 should be the answer. Rounding for 5, all that stuff. And then likewise, for subtraction, if I have 158.1 minus this, yeah. It's amazing how the simple rules that you carry to one. Whatever. Okay, so 72.96, that should be, you can say 72.9 or 73.0, whatever suits your fancy. I'm not going to be too particular on the rounding. So, no, it's going to be one digit after the decimal. Oh. Right. So that's your reported answer, but the calculator says 72.96. Okay. The next thing we covered was units, unit conversion. You can reference your chart. I'm not going to show it here, just going to briefly talk about that. At the chart, I know I have it here, but I won't quite look for it. Yeah, waste a little time there. So referencing your unit conversion table, you know that in order to convert from different types of units or the same type of unit, femto to pico, peta, whatever the case was, if you, right. So you want to start at the unknown quantity and count powers of 10 up to the known quantity. If you're counting to the right on your chart, then the powers of 10 will be positive. If you count to the left, it will be negative. So in order to convert different types of units, where in the middle of the unit, middle of the chart, it should be meters, grams, seconds, Teslas, joules, coulombs, whatever the case may be, a baseline unit, and we want to convert in different types of the same unit. We start at unknown. And count powers of 10 to the known. How many centi unknown are in 1 meter? 2 powers of 10 to the right, so it's going to be 1 times 10 to the second, or 100 centimeters in 1 meter. So that's a thing. Yeah. How many, the question mark, how many centi in 1 meter? We take the given, the number there, and we ascribe the powers of 10 to the right, and it's 2 powers of 10, 1 times 10 to the 2, or 1 times 10 to the second, equals 100 centimeters in 1 meter. And likewise, if I want to figure out how many meters there are in 1 centimeter, then it's going to be 10 to the minus 2, 0.01 meters in 1 centimeter. So we just switch the sign. So therefore, if you count right, it's in terms into the positive x, whatever x is, 2, 15, 39. And then if left, it would be 10 to the minus x. You see that on your chart. I have the big long arrows. Going to the right, that's 10 to the x. And going to the left would be 10 to the minus x. Right? So that's what we got. And pausing a second. Now what I want to get to is the lab report schema. And I want to share a screen here and just kind of go over this. I'm going to post this on the Google Classroom because this is going to be basically the schema or outline of how like all lab reports. In the first couple of particle models, if you will, the constant velocity particle model and the constant acceleration particle model, of which you can see some results and charts, whenever you look over there on the wall there, you will see that most of this schema in those particle models are pretty much embedded in the lab itself. So generally what we're going to do, especially when we get to the CVPM, we're going to start off with basic definitions. Definitions like position, displacement, distance, time, velocity, acceleration. So we'll start off with that. Preliminary information, a priori knowledge that not only will help us for the lab, but it will also, help us with our book work and all that good stuff, which is coming up fairly soon. Next, we'll start off with observations. What did you see? What did you measure? Are there any other observations? So for example, I'm going to have this constant velocity car that allegedly moves at one particular speed. I'm going to have a meter stick and then be asking you a question. What can you measure about this, this car with respect to the meter stick and anything else? What by looking at that apparatus, what can you actually measure? What can you actually put down on paper? Or probably measure the length of a car, or you can measure something like position. We'll investigate that. So that would be observations, or observations that typically lead up to a hypothesis. You might be seeing this quite accurately enough, English accuracy, that this is the scientific method embedded within a lab report schema. It's all pretty much the same. I'm just embedding those concepts. We then go to hypothesis objective. What kind of relationship is there between the quantities you measured, or what do you believe is going to happen? Based on what I see, observations, I believe that this is going to take place. Hypothesis, and then you go to test it. That falls under the interpretation of results part of the scientific method. We then get this data and we put it into a data table. And that's what we're principally going to be talking about today. This idea of data table of results, independent, dependent variables, linear and non-linear data. We'll be talking, we'll be definitely have to understand what is the difference between data that's linear and data that's non-linear. Right. So you'll probably intimate that linear data has everything to do with a best fit line. It's linear. But, you've seen that before in your algebra class. Non-linear, we're going to see that with acceleration and all that good stuff. So I think we get down to the bare bones of what is independent, dependent variable. I'm sure you've heard of that before. You've done that in your bio classes, somewhere before, more than likely. Then we will have calculations, data calculations from the data tables, graphs, equation of a line or curve when we get nonlinear results, standard deviation, standard error, and even percent error. Put this in there. There's all kinds of data manipulation that you can use for your results. Percent error, percent difference, variance, but we're not going to get crazy. We're just going to do kind of the basics, standard deviation, standard error, percent error, equations of lines. And any questions that you may, you can propose to another group, and any conclusions. We'll pretty much most of the time just go to conclusions. So this is basically a lab report, lab schema, scientific method embedded, and we'll get used to this over time. So let me go back to prior screen and talk more about the lab report schema. Okay, so our first lab or first analysis, project would be the CVPM. I'll be posting that up next day or two. So I want to get started with that hopefully this week, definitely by next week. But this week, I want to start off with definitions, a priori information, so that we can go into the CVPM with some sort of working knowledge of what we're actually looking at. Otherwise, we'll be just kind of throwing mud at the wall. We want to know what we have, some basic tools for this. So first lab is CVPM. Before we get into the meat and bones of that, I'll start off with definitions like position, displacement. You will find those in your second chapter of your book. So we're going all in line. The method is unimportant. The content is important. So we're gonna touch bases on everything. Position, displacement, even distance, say speed, velocity, time, and even acceleration down the line, force, energy. We're going to get to all those things. So we're going to start off with basic definitions. These guys here. The next time. So like I mentioned, we will have situations in the lab. What did you see? What can you measure? What kind of relationships are there between what you can measure? Is there a relationship? And then we get down to getting all those measurements and placing them into what we call a data table. Now, typically, like I like to have a data table, I like to have my information that I'm going to place on my vertical axis on the left side of the data table and the x-axis on the right. Let me show what I mean. Y-axis data here. And then I have my x-axis data over here. So typically the information in the vertical axis, the y-axis, is going to be my independent variable. Sorry, no, that would be my dependent variable. So, and I'll explain all that here shortly. So my dependent variable is going to be in my left data table column. Independent variable in the right column. What are those things? The dependent variable is the variable that you can manipulate in an experiment. And we'll find that you can manipulate position. You can manipulate force. You can manipulate certain physical quantities. And any quantity that you're going to manipulate is going to be in the left column. And therefore, the variable or the results that you can't manipulate are going to be in the right column. Those are the independent variables. So let me just briefly pause at this case. The dependent variable is the variable can be manipulated. This is the one that you're controlling or you're measuring or you're doing something to it. You're manipulating. An independent variable cannot, that you leave alone or you don't manipulate it. The dependent variable, well, depends on the independent. So it's always the variable that you are working with, that you're controlling, that you are manipulating. And you guys have done this before in your other classes, biology, chemistry. I'm sure it's in some point you've had some exposure to that, hopefully. All right. So what we're going to see, that being basic definition, in the CVPM, that it's going to be two quantities. I'm kind of giving away the answers of what we can measure and what relationships we can form. The variable that's going to go into the dependent or left column of the data table is going to be our position data, which we denote with the variable x. That, again, I'll stretch that out when we go into definitions of position, displacement, and all that stuff when we get there. But this is just for example purposes. The position will be our dependent variable. Time will be the independent variable. And time is always going to be independent. That's going to be the variable that we choose not to control. It's just going to be there. It's something that we measure. But we're not doing anything to time. A position we're manipulating. Now let's say that in this particular data table, position versus time, we have our little position constant velocity car at 0, typical. We're starting everything starting from scratch. It's time 0 and position 0. And then let's see what we're going to see something. We're going to observe something. We're going to measure it. And then we say, like, after the first second, let's say that the car is at 2 centimeters, the same. And let's say at the second, it's 4, 3, 6, and you see where this is going. Every second, it increases by 2 centimeters. We have our centimeters. So velocity speak, we're going to get to that. We can say that the car has a velocity of 2 centimeters every second, because every second it's increasing its position by 2 centimeters. And we're going to do something else with this in terms of the linearity or non-linearity of this data. We're going to determine which is which. And I believe you guys are smart enough, you can see this, where this is going. You know what kind of data this is already. Anybody out there want to take a guess? Is it linear or non-linear? While you're thinking, I got a quick question. We are supposed to be writing it all down. That's right. And it is linear. Thank you, Mo. Totally linear. And I'll tell you why. The basic idea of linearity, the gaps in the dependent variable. You can look at the independent, sure, but the dependent variable, the gaps are the same. If the gaps are the same, the data is linear. It doesn't matter what it looks like on your plot, right? If it's, you know, if you have points here and all that, and you're trying to connect them, but don't ever do that. You look at the data here and determine if it's linear or non-linear. The gaps are the same. 2 to 4 is 2, 4 to 6 is 2, 2, 2, 2. Every second, it increases by 2 centimeters every second. So this is linear. The gaps in the dependent variable are the same. Therefore, it's linear. If it's not the same, it's nonlinear. In the case of acceleration, in the first second, we could go 2, the second we could go 7, and then we could go 15, and then we could go 33. Then the gaps are increasing. They're not the same gaps, and therefore that data would not be linear, it would be nonlinear. But anyway, we're just going to stick, well, with this principally in the first couple of days or so, but I did introduce both terms, linear and nonlinear. But so this data table, and we'll see if this guy holds up nicely. And then I should have ordered some other ones, but we'll do what we can with that one. You'll see that this cart might not go 2 centimeters every second, it might go like 5 every second. It just depends. But let's say that this car goes 2 in the first second, and then 4, and 6, 8, 10. This is very linear. This is a best fit line. The slope is constant. This data table here, and again, we'll go this when we see the context of the CVPM. This data table here has a constant slope, linear. So just to repeat, linear data. Gaps, I'll say in the dependent variable, the gaps are the same in the left column. Always look at the left column. What's going on in the left column? Gaps the same, linear data. Gaps between the numbers, 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10. And then nonlinear when the gaps are not the same. And we are going to see for nonlinear data cases of acceleration and deceleration. For acceleration, the gaps are going to increase in a nonlinear fashion. And for deceleration, the gaps are going to decrease in a nonlinear fashion. That means that, for example, I mean, at some time you can see at one of those CAPM labs where we're going to have curves that are increasing and then curves that are decreasing. We'll understand how to look at those and understand which part of the graph is actually accelerating versus decelerating. So you're going to see that because cars speed up. If I push a car in the object in class, due to friction and all that good stuff, I'm going to have a moment where the car is going to speed up and then it's going to slow down due to friction. I'm going to have an increase and I'm going to have a decrease in the gaps. So non-linear gaps are not the same, increasing or decreasing, right? It doesn't matter how it won't even matter. If you plot those points every second you put on any type of graph, however you're going to scale it, you know that for a nonlinear case, you're going to be drawing curves, not lines, because this is non-linear. There are no lines. There are just curves. And we're going to understand how to draw acceleration curves and deceleration curves, right? Okay. So the gaps are increasing or decreasing. The left column. Because you can still have time. Time's not manipulated. Time's just going. 1, 2, 3. I'm accelerating or decelerating. 4, 5, 6. And so that's the basic idea. And so we're with the CVPM, we're going to be working with linear data. You know, trying to give it away. It's a context that we're going to be in. Now, that's long and short of it. I can give a few examples now. We just have one example of linear data. So let's say this is a giveaway now. Let's say I have a data table with the position in centimeters and then time in seconds. Or XT, a position time data table to produce a position time graph. Let me show you the nonlinear case. 0, 0, 2, 1, 7, 2. And then, you just keep expanding. This would be the case. The gaps are dramatically increasing, goes to 2, then 5, then 11, then 17, and then 26. This is a case when the gaps are increasing, as you see on the left. This is a case of a car that's accelerating, speeding up. And then conversely, if now we're continuing on, let's say we go, we in 35 to 61. Oh, let me just do this over here. That'll be probably nicer. So that's accelerating. And then we have time in seconds here. This would be, so I'm going to continue from 61. Just continuing. Not exact with that. Let's go in the 6 second, it goes down to it's 75 in the 6 seconds. And then we're going to go to 83 and 88, 90, and still increasing position, but the gaps are decreasing. So from 0 to 5 seconds, the car is accelerating, it's speeding up. And then from the 6th to the 9th second, it's slowing down. The gaps are getting small. Any questions on that? Seem all right? At least the basic concept. We'll explore it in detail when we get to those labs. Sliding. You usually go to 10 seconds. But so yeah, so this is all right. I'll just squeeze that in. So we go, yeah. So this is deceleration or slowing down. And this is acceleration or speeding up. We will then see in time that there are three types of graphs that we're going to be graphing. There's going to be a position time graph leading to a velocity time graph to an acceleration time graph. And if we have a case of either acceleration or deceleration, we're going to see that we're going to have all three. But when the speed is constant, we just have two. We're just going to have a position time graph and a velocity time graph. And we're going to really understand how to go between all of them, all of those. So when you accelerate, put your foot on the gas, you speed up and put your foot on the brake, go down, the position shortens, tightens. Yeah. Let's see. That's pretty much it, at least for, this is a little bit longer than I promised, but 1 second. So next what we have here is what we're going to call a position time graph. Again, all of the stuff in the lab report schema, we're going to do again when we get to the actual lab. This is just the intro, as it were. Position time graph. So now we are going to put, as I mentioned before, all the data in the left column is going to go on the y-axis, the vertical axis, and the data on the right column, the x-axis. So our position time graph is going to have, well, t for time, and we have the units seconds, and x the centimeters, because we're typically going to measure our car in terms of centimeters, positions. So our positions were 0, 2, 4, 6, 8, 10, and then 1, 2, 3, 4, 5. So we plot the points, and of course, it doesn't have to be exact. I wouldn't be too worried about all that. That's a pretty neat almost line there. But now, since the data is linear, well, we draw a best fit line through the data points. They don't have to connect. A little space up here, but yeah, so a line of best fit. You're not going to connect all the dots. Do not connect the dots. If they fall off axis, who cares? A line of best fit, because the data is linear. Now, we will then see too, when we get to the CVPM, that the slope of this graph will produce a new physics variable that we call velocity, average velocity. And we'll again come to terms with what that is. So when we go from here, a line of best fit, the slope of this graph will give us velocity. I'll leave that, I'll belabor that point next time. So this is what you do with the data table. You're done there, position time graph. Now, let me go to the nonlinear case. So we have another position time graph. I'm going to put all the numbers there. Well, now that you've grabbed all of your data, you put it in your data table, you've determined that it's nonlinear and the gaps are growing, the gaps are increasing. So what you do in that case, you're going to draw a best fit curve that that shows that the car is increasing position dramatically. And so in this case, we will have a curve that looks like something like that. And if you go and compare CVPM, we're going to have motion worksheets and all that stuff to make sure that we understand that this is an acceleration curve. Dramatically growing position. And this would be the graphical depiction of a car speeding up or accelerating. And then we go to velocity time. We know how, we're going to see that the velocity is going to increase as we're speeding up. And then the acceleration is going to be constant because the slope of that velocity is going to be your acceleration. We'll get to all that. But they're just doing the basics. This is what it basically looks like, the position time data for acceleration. And then I'm just going to abbreviate position time. Those are the variables for position time. We will become comfortable with this. For position time, for a decelerating case, the curve is going to look something like that. So again, not to worry about that first day out, but this curve would be what is known as a deceleration or slowing down curve. In either case, gaps are increasing here, and then over here, the gaps are decreasing. So we're still increasing position, but it's steadily getting smaller and smaller. So like this right here, this point could be your 88. And as you can see, it's not trending up as high. This could be like 90. So the gaps are getting, the slopes are diminishing and they're tending towards zero. That basically means in physics speak that the velocity is going to zero. It's trending towards zero. It's coming to a stop because you have the brakes off. So this is just a picture of that, graphically speaking. And of course, the one on the left, that's going to tend off to infinity. The one on the right is going to have an asymptote somewhere, and it's just going to approach this final slope of zero. So yeah, it's not logarithmic. But yeah, I mean, that's just the basics. So we have now our data here. We graphed it. Going back to my lab report schema, I'm in the data table part. Calculations will be next. So I have my data table of results, my independent, dependent variables. My dependent is on the left, my independent's on the right. Linear, nonlinear data, we've determined that. And so now we go back to the position time graph, the linear data, and we make some calculations, maybe some equations. We go down to the next part. Equation of a line, standard deviation, error. Again, when we do the labs, we'll do it so many times, you'll know what will happen. But just the introduction. So I want to go back to this graph here, and I want to do an equation. I want to derive an equation from it. I can. Back in algebra that the point slope equation, blah, 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 of a form of this, the equation of a line form is basically this, y equals mx plus b. So when we go to real physics terms, we have to now take just not the arbitrary y-axis data, we have to make that into a real physical data, which is, in this case, the real data in the y-axis is going to be our position. When I just want to say y, I'm going to say what y is, which is x, position. That's the variable for position. Agreed upon variable. So we are going to go from the algebra point slope equation of a form of line to x equals, and we'll find out very shortly that the slope of this line is going to be called something physical. The slope of this line is going to be called your velocity. So instead of putting m, we put v for velocity. We'll see that when we get there. We go from m to v, and then the variable on the x-axis is time. We don't say X, we put T. And there is no y-intercept. So in this case, the equation of this line is X equals BC. Okay. This is the physical equation of this line. No y-intercept. You can say plus 0, but leave it out. And the equation of the curves, the accelerating and decelerating, that's a little bit more complicated. We'll leave that out because it's going to take us into the weeds. So we'll do that when we need to. Yeah, that's the basic thing we want to work with. You're going to see the CVPM packet, so I would definitely take a look over this again. But we're going to do this again, in the next lab. Let's see. Oh, okay. So we did graphs, the equation of a line. I'm not sharing the screen at the moment, but equation of a line or curve, standard deviation, standard error, percent error. I'm not going to belabor the point with standard deviation and error, but I'll do an example of percent error. Okay, and that'll be the last topic, and then we'll be done. I know this is intended to be long because we'll make sure we have our introduction and try to make everything else within 30 to 40 minutes. But thanks for hanging in there. Okay. So concept of percent error. Anybody heard that? Percent error. Seen that before? Good, good. So bio or chemistry? Yeah. Okay, you've seen it. Great. So really what percent error is another data manipulation to determine how well our experiment went. If our percent error is very small, good experiment. It's like above 50%, let's go back and change some things around. Because the number will tell you what went wrong, it'll just tell you that something is wrong. Right, so like if let's say our accepted value for gravity is 9.81, and then we got an experimental value. We went to the lab, and our experimental value is 9.6. Okay, then we do a percent error, which is the difference between the absolute value of the difference between experiment minus known divided by the known, I should say, known here or accepted. Accepted is the same thing as known, K, experimental, and you multiply this whole thing by 100. This is going to be a decimal. And so a sample percent error would be 9.6 minus 9.81. You can never have a negative percent error because it's a number. That's why the absolute values are there. So 9.6 minus 9.81 over 9.81 multiplied by 100. And that's going to be 0.21 absolute value. Okay, that's 0.02. Multiply that by 100, 2%. So that's very, very good. I mean, if you can get something within 15 or less, that's an excellent experiment. So this would be a sample percent error that we're going to be including in our labs. 100 equals roughly 2.1% for experiment error. Now, if your experiment results was 4.8, you're going to have a high percent error. You have to go back and the number will just tell you that something's wrong. You have to kind of go back and be a super sleuth and figure out what actually went wrong. Why did you get 4.9 as opposed to anything closer, 8.8 or 9.6? That is pretty much all on that percent error. Then at the end of your lab, as I'm going to show here, the end of your lab, we don't have any questions per se, but if you have any questions, you can put that down. But conclusions, like what did you take away from this experiment? What did you learn? What were some obstacles that were in the way? You know, some things that you enjoyed about the lab, or some things that you got right, got wrong, all that good stuff. Or some, yeah, just kind of like evaluation question. So yeah, that's pretty much it. Okay. Possibly have that for the next people. Okay, so in-class problem, the radius all right, the radius of the planet Saturn, 6.03 into the 7 meters. And its mass, 5.68, 10 to the 26 kilograms. All right, so you have that. And the first question is, find the density of Saturn in grams per cubic centimeter. Not kilograms, but grams. So, you know, from chemistry, density is mass over volume. You have the mass, now I'm gonna get the volume, and you're gonna assume that Saturn's a sphere. Perfectly, one, but assume it is. Find density of Saturn in grams per cubic centimeter. Okay, we're gonna do some fancy conversions because remember, we don't want to use kilograms per cubic meter. That'd be the easy part. So we need to convert kilograms to grams, and then meters cubed to centimeters cubed. Okay. All right, you guys are working it out. Okay. Remember, volume of a sphere is 4/3 pi r cubed. I'll just let you have a stab at that one because there's a part B, but we'll leave that one out. Because the part B is find the surface area of Saturn in square meters. That might be a little easier because then you don't have to do any conversions. I'll put it up there just in case, you know, all you smart people, you're all smart. Both of these. Find surface area. Saturn. Anybody know the surface area of a sphere? Remember that? No. 4 pi r squared, right? 4 pi r squared. Expect you guys to provide all these. All right, so that's it. Should have plowed that over, but this is the part A is the most important. Radius of Saturn, 6.03 times 10 to the 7th. The mass is this. Find density. And remember that density. Squeeze it here. Here. Usually by some books say just D. Rho equals mass over volume. This is density equation. Okay, and that is that.